In this series of webcasts, I'd like to take you through some of the things that Jmol can do and some of the more common workflows that you'll find yourself engaging in as you manipulate your structures. And the example I'm going to use is that of carbonic anhydrase, which is an enzyme that catalyzes the decomposition of carbonic acid into bicarbonate and proton. As you might imagine, this is a rather important process, especially for those of us who like to drink soda, as soda is full of both carbon dioxide and water. What you can see on this Wikipedia page is that a very nice rendering of the active site of a carbonic anhydrase is here, but this is a far cry from what you'll see on the PDB. So PDB reference is given here, and if we visit that PDB, you'll notice that even on the website, the default structure looks very simple and lacks a lot of information. We need to use what are called Jmol scripting commands in order to manipulate the structure and make it look the way we want it to. Now let's see if we can turn the structure shown here, 1Ca2, into that very nice active site picture that we saw on the Wikipedia page. The first step to any operation in Jmol is figuring out what you want to do. In other words, form a picture in your mind's eye of what you want to accomplish and use that picture to guide your thinking and searching as you look through lists of commands and parameters and the like. In our case, we'd like to emphasize the active site of 1Ca2. How can we go about doing this? Well, as you'll learn, there's a command in Jmol that strips away all of the bonds and atoms and leaves a very simple cartoon view of the protein behind. We should probably start here, and then from here we can add the wireframe view for the actual residues that are in the active site. That way we can really think specifically about the chemistry of the bonds and atoms only in the active site, and in that way our Jmol will achieve its purpose. By navigating to File, Output Console, I can open the Jmol script console. This is where the magic happens in Jmol in terms of actually manipulating your structure. And that's step 2, manipulation. After forming an image in your head, the next step is to actually make it happen. And we can break manipulation down really into 2 separate sub-steps. The first is selection. The first thing you'll always want to do with a Jmol structure is select the atoms you want to manipulate. A very common domain of selection is simply every atom in the molecule. To select every atom in the molecule, type select all. You won't see anything happen, but in the script console you will see the number of atoms that have been selected. There are a variety of different keywords you can use to select different atoms, residues, or structures within your structure in Jmol, and these depend basically on the organization of the file that you're looking at. Files from the PDB are highly organized, and so they'll have everything in terms of atom numbers, residue numbers, and structure numbers built in. If you create a file yourself, you may not be able to use some of these built-in keywords. So for instance, every file, including those you make yourself, possesses atom numbers. Every atom in the structure possesses a particular atom number, which is abbreviated in Jmol as atomno. For proteins from the PDB, some of these atoms may be grouped together into different residues. You can access the residues by referring to the resno keyword. So for instance, if we wanted to select residue number 3, we would use the command select resno equals 3. Residues are built into larger structures, which are called in Jmol simply structures, and you can access these by using the structno keyword. Structno refers to the number of the structure in terms of the primary sequence. So the very first helix or sheet is structno equals 1, second is structno equals 2, etc. And finally, for quaternary structure, entire chains are encoded into PDB files. And if you wanted to access a particular chain, you could use the chain keyword. Chains are usually lettered rather than numbered, and so they start at A and go to B, C, D, etc. It's possible to combine selection domains using logical operators, and it's important to understand how to use the logical operators to really achieve what you want to accomplish. So if you wanted to actually select, for instance, serines and histidines within a structure, you would actually type select ser or his. This is because the set of objects returned by this statement possessing the residue designation serine or histidine includes both histidines and serines. If you typed select ser and his, then you would receive a set of residues that contained the designation both ser and his, which turns out to be nothing. So this would lead to nothing being selected. With the selection phase complete, the next step is the makeover phase, and here's where you're actually going to influence the appearance of what's in the window. There are all kinds of commands to do this, but in our particular case, what we want to do is focus on the residues only in the active site. So let's take the entire structure, turn it into a simpler view, and then only show the ball and stick view for the residues in the active site. To do this, we can select the entire protein, type cartoon only, and then find the active site by noting from the Wikipedia article that there's a zinc atom in the active site. So by typing select zinc spacefill 80, you can see the zinc atom appear at the center of the structure. At this point, we're back to the selection phase. We've made the zinc atom appear, but now we need to select the rest of the active site, which according to the Wikipedia article is 3 histidine residues around that zinc atom. There are a couple of ways we can go about doing this, but regardless of the way you choose to go about doing it, it's still this same general procedure of visualizing, selecting, and then making over. So visualizing the 3 histidines, we see that we need to select those and turn on the wireframe and spacefill for those atoms. To select the histidines, we could either determine their position in the primary sequence, or we could look for atoms within a certain distance of the zinc atom that are also histidines. And so here you'll see an example of using a logical operator to combine properties and get a very specific selection out. Using the select within command, I can select atoms within 6 angstroms of zinc, but I also want those to be part of histidine, so I can also say and his, and we should only see atoms from histidines appear. For visual confirmation, let's spacefill those and see what happens. Aha, and we can see that 3 histidine residues have appeared around the zinc atom. If we want to know the residue numbers, we can simply mouse over each of the side chains to determine it's 94, 119, and 96. You can do a lot more with Jmol than what I've shown in this simple webcast. In fact, we want you all to be creative, and so feel free to use all the resources at your disposal in order to make over your Jmols in the most creative way possible. There are a variety of resources available out there on the internet for you, including the Jmol tutorial that we've put together that I'll cover in the next webcast.